Hello, welcome to SOH, the best ever office hours in the universe, thanks to you. And thanks also to the AP test, right? That's why we're here. But anyway, let's have some fun with this. So the function f has derivative. This is, 2023, Calculus BC, question number 6. Let's go over, and then I hope that in a couple of minutes you have clear ideas of how to deal with these problems. It's kind of a different problem compared to other ones, so it has some interesting things. And yeah, then you can see how I solve it. Indeed, the official solution missed a little thing, nothing really dramatic. So we're still all alive. But yeah, I think that they could have written a better solution for one of the questions. Nothing dramatic, I say, but you can learn a bit more about it. But let's go. We have a function and has derivative of all orders. This is also called C infinity. So C infinity, but that's just like a bonus. It is known that the function, this is important, right? We want to highlight here that we know something about it. Value at 0 is 2, the derivative, the slope at 0 is 3, and then it has this special relationship, which are pretty cool, right? A little bit like, ooh, what's going on here? But anyway, that's how it is. And then first question, find the fourth derivative. Okay, nice. And then write the fourth degree Taylor polynomial. Okay. About x equal to 0. Of course, show all the work. Always. Even, I don't know. They always ask, because otherwise people, I don't know, they just write one thing. But always show your work. So, fourth derivative. Well, one more derivative. You will start with this and take one more derivative. You will apply the product, the rule for the product, and then the chain rule for this one, and you will get the fourth derivative. Then you will substitute at x equal to 0. But what is Taylor polynomial? Taylor polynomial is, let's say, of degree n of a function at around 0. So this is interesting. Around 0 is the same as the Maclaurin series, okay? That has this name. But anyway, Taylor, if it is Taylor, the Maclaurin series is at around x equal to 0. There will be a nice proof that indeed they're equivalent, Taylor to Maclaurin, because you can always make a change of a translation. Right, you can move your function to another point and do everything there. So it's not the same function, but just with a simple translation, Maclaurin deals with everything that Taylor does. Anyway, so you start here and you take your function. Let's say f is 0, then the first derivative, then x, and so on. Let's write one more term until you get to the nth term, and there you stop. There is no low dots or at a higher orders. No. This is an exact polynomial. It's not an approximation of the function. Of course, this polynomial is an approximation of the function, but the polynomial itself is exact. So you end up here. Okay. What else? Then the fourth degree Taylor polynomial about x equal to 0 is okay. That makes sense. It's close, right? And then they tell you that if you know that this is true, then compute that the Lagrange error bound is within this, which is, wow, it's one part in 10 to the 5 in 100,000. That's a pretty good approximation. Also, this number is very close. But anyway, that gives you an idea how these polynomials can be helpful sometimes. What is the Lagrange error bound? Well, it's a formula that we have. You take the n derivative, which is the next derivative. If you have a polynomial for n, it will go to n plus 1. So maybe you want to have here n plus 1. Depends on what you see at school. Then here there is C, and I will tell you C is a point under consideration. So it's like C would be between 0 and indeed 0.1. So there's exists a number C between 0 and 0.1. And then you have here delta x. Delta x is the interval that you are considering. So here would be 0.1 to the power of n plus 1, and then n plus 1 factorial. Basically, if you look at this, it's the next term, right? It's just the next term of the polynomial. The error that you're committing is that, but with this detail, it's not at 0. It's a point between your interval of consideration, okay? And any, you don't know which. So that's why they tell us that for any of these x, this holds, even for a larger bound. Okay, fine. So you will use that to constrain this and get that is 10 to the 5. And then this is a very interesting problem. Has two ways of doing it. One of them is to say, okay, the second polynomial is going to be, this is g, right? So g of 0 plus g prime of 0 plus g second derivative of 0. And there is no more terms. No low dots, etc. Okay, it's just it. So notice that g of 0 is here. G prime of 0, well, you just substitute here. So the only deal is to compute the second derivative, which can be done with the product rule and the chain rule, and substitute, and that's it. And there is another way, so that's it. That would be 5 plus. But there is another way. Another way is also saying, well, if I have to get to know g of x to second order, then I have to get to know g prime to first order. Is one derivative x squared is x, right? So you can use an approximation of this function to first order, which is simple, and an approximation of our f to first order that we already got it, or we could just do it because we have f prime here. So we know that this is going to be 2 plus 3x anyway, f of x, just to be very fast. Then you multiply this, you keep only first order, you integrate, you use this condition, and you get the polynomial. That's a bonus, and that's interesting in case that, sometimes if you think beforehand, it may be faster to do it in one way or another. But that's just a bonus. Okay, try to solve it and come back when you have your 5 and you want to compare your way with my way, and let's continue to see how we solve each of them. So the first problem says find the fourth derivative. Okay, that's exciting. So what we have here is, let's compute the fourth derivative. Let's be Roman. Romans didn't compute derivatives, but anyway, that's how it is. And then we have here prime, so one more. And then what we do is to apply the product rule. Minus 2 multiplied by this derivative, awesome, minus 2x, and then this derivative is going to be the second derivative, and then multiply by 2x. Now here there is a minor thing that is not accounted for in the college board solution, and it's the following: is that they leave it like that, but we know this, right? So if we know that f of x, the second derivative of x is this thing, then guys, the second derivative for this is this. Okay, so what we can do here, which is much cooler, is to say, okay, this is minus 2 f prime of x squared. F prime doesn't have any simplification, so it's minus 2 minus, let's write it all together, right? 2 and 2 is 4, minus 4x squared. And then this second derivative is plus, and this, right? That's, I think, a better solution than that one, because we use what they tell us, basically. I mean, both of them are correct. There is no, like, dramatic, the world still spins, and tomorrow we will still need to wake up. But, it's a better way to be consistent with what they tell us. Okay, cool. First part. Woohoo. Now, the fourth degree polynomial. Well, the fourth degree polynomial, as we were talking, is an exact representation of the function as a polynomial, but without considering the higher terms. So it's like, okay, the function at 0, because remember it's around x equals to 0, f prime of 0 times x plus 1/2 of the second derivative. We're going to write a little bit here, plus, 3 factorial, the third derivative, and then finally, right, with our fourth derivative. What I mean by exact, I mean that we stop here. There's nothing else. End of the story. It's not plus low dots, plus higher order terms. It's an exact, description of the function with a polynomial. So of course we are going to miss something about the function for sure, but that's the polynomial, and as a polynomial is exact. So now we have to get to know how much is f, this one, this one, this one, this one, and this one, right? So let's see. We have a little bit of a space. Okay, let's just do a new page. So what we have is, okay, f of 0, it was given in the problem, right? It was 2 and 3. Okay, so f of 0 is 2. Yeah, I don't want to cover it with my face, so it's here down. F prime of 0 is 3. The second derivative at 0, well, we can use the famous relationship here, right, or here. So it's going to be minus f of 0, which is minus 2, right? The third derivative at 0, I think we will like that more because it is, what is the third derivative at 0? But we have it here, it's going to be 0, 0 times something, so 0. And finally, the fourth derivative of 0, we can use our famous expression here, minus 2f prime of 0 plus 0. So minus 2 times 3 is minus 6, right? So with all this information, we can go back and say, okay, this is the value of 0, 2 plus 3x. Now the second derivative, minus 2x squared divided by 2, don't forget this. The third term is going to be 0, and then plus this derivative, minus 6, and then divided by 4 factorial, which is 24, right? So, and then x to the power 4. So basically, we get that our super polynomial is this thing, which is amazing, okay? Beautiful. And that's it, nothing else. Perfect. Let's see what comes next. Okay, yeah, this thing about the error, right? It's a little bit confusing, but this Lagrange error bound, you have to compute it like this. It's the fifth term, so it's the next term. So it's going to be some derivative of some point c multiplied by this difference. Well, it's 0.1 because we start at 0, but you know, it would be delta x, whichever difference it is. Imagine that you would expand the function about 0.3, and you estimate the function at 0.4. Delta x would still be 0.1. So you have 0.1 to the power of 5, and then divided by 5 factorial, right? Okay, now notice that 0.1 is nothing but 1 divided by 10. So we have to get something close to this expression. So that's why we do this. 0.1 to the power of 5 is going to be this. So basically, if we can neglect this, we're good. Now, how much is f5 of c? C is a point that lies between 0 and 0.1. We don't know which one, but we have this thing that it's always less or equal to 15, even for a larger interval. So this is going to be less or equal than 15 times 1 10 to the 5, right? And then 5 factorial here, okay, which is 120. And then you want to get to this expression because it's the one that they have here. So basically you want to get rid of this, but this guy is less than 1, right? I mean, indeed, is equal to 1/8. So this is actually less than 1. And then, you know, super awesome, and then we're done. Okay? Excellent. Yep. I mean, it's a very nice approximation, 1 part of 100,000, but it's also close to the solution. And now we have this one, which is a pretty cool question. So this one, there are two ways. The fast way, is to say, look, so what do you want? So this is the Taylor polynomial of g, okay, g, not f. So this is going to be g of 0 about plus g prime of 0 plus blah, 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 blah. Okay, thank you for listening. And then g0 equals 4. G prime 0 equals e to the power of 0 f of 0, which is f of 0, right? Because this is 1. And f of 0 was 2, thanks to the wording. Now, the deal is to compute the second derivative. But we can apply the product rule, right? So it's going to be this thing, and again, another derivative. So the first derivative, then another guy, this guy, and this guy. And then the second derivative at 0 is 1 times f0 plus 1 times f prime of 0. Remember, this is 2 and this was 3. Thank you to the wording. So this is 5. So we have everything we need. So let's write the super polynomial. So what we have is g of 0 is 4. Let's choose another color just for fun. So green, 4 plus g prime of 0. What was that? 2. Oh, look at that. Let's add here an x, right? So what are you looking at? Good. So 2x plus 1/2 of g, the second derivative is 5x squared. So here you are. You know, if you like, you can write this like a fraction, you know, like a fraction, like that, and that's it. Okay, and this is fantastic, A++. Now, there is additional, but this is absolutely optional. Another way of solving this problem, which I think is cool. And because sometimes it will be good that you know this kind of things. For instance, e to the power of x is 1 plus x squared divided by 2. Sen of x is approximately x minus x cubed divided by 6 plus, you know, higher order term. Cosine of x close to 0 is this, right? Blah, 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 and other relationships. So or I don't know, the square root of 1 plus x is approximately 1 plus 1 half of x, you know, blah, 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 or logarithm of, I don't know, 1 plus x is approximately x, things like that, okay? So these are all for very small values of x, okay? Now, why is this helpful in our case? Well, we want to get to know the second order polynomial that corresponds to g of x. And what we know is g prime of x is this thing. So if this is second order, right, then the derivative is which order? First, like you, first, okay, first. So as far as we write e to the power of x like a first order, which is that simple, and f of x to first order, which I remember by memory is this, but otherwise we can't review it because it's f at 0 and f prime at 0, but let's review it. We have our super polynomial. Where's our super? Here it is. Then that's it, because you can multiply this and get g prime of x. To which order? Only first order. We only care about first order. So if you multiply these two guys, 1 times 2 is 2, 3x plus 2x, and no more, because it will be x squared, so it's first order. And now you have that this is this. Of course, it's longer than the other solution, but it's cool. And then this is the integral, right? This is just the integral. So you're going to get that this is approximately 2x plus 5 half of x squared plus a constant plus unknown terms that we don't care because we are looking for the second order polynomial. Now, this is important, but you know that g of 0 is 4 according to the wording, right? Here it is, or somewhere here. So now with that, we will find c. And, well, c is 4, right? So you have that g of x is approximately 4 plus 2x, I'm just reading everything is correct, 2x plus 5 halves of x squared, okay? And, well, plus, but the second order polynomial that corresponds to this is just this, exactly, nothing else. And so you have another way of deriving it, and then let's compare. Yes, it is the same, of course. I mean, yes, we are the best. So that's how it is. Okay, see you in the next one. Okay, let's knock all this out. Bye.